Welcome to G-Fun Facts Online, the world of pure mathematics, a realm of abstract thought long considered the exclusive domain of human genius, is being quietly revolutionized. It's a revolution not of chalk on blackboards, but of algorithms and silicon. Today we're exploring how artificial intelligence is moving beyond simple calculation to become a creative partner in mathematical discovery, forging a new era in our quest for universal truth. The dream of a machine that could do mathematics is almost as old as the computer itself. It all kicked off in 1956 at Dartmouth College, where the term artificial intelligence was born. There, a program called the logic theorist was unveiled. Its goal was audacious: to prove theorems from the legendary mathematics text Principia Mathematica. Using a clever approach of working backward from the conclusion, it successfully proved 38 of the first 52 theorems it was given. It even found a more elegant proof for one of them than the human authors had. The creators called it a thinking machine. This early success sparked a debate. Should AI try to mimic the messy, intuitive way humans think, or should it use its own, brutally efficient machine-oriented logic? For decades, both paths were explored. Computers became essential tools for brute force calculations, most famously in the 1976 proof of the four-color theorem, which required a computer to check an enormous number of possibilities, far beyond human capacity. But the creative spark, the act of dreaming up a new idea or a new strategy, remained firmly in human hands. That is, until the deep learning revolution gave AI something that looks remarkably like intuition. Perhaps the most profound impact of modern AI is its ability not just to prove what we know, but to suggest what might be true. In 2021, a landmark paper in the journal Nature revealed a stunning collaboration between mathematicians and Google's DeepMind. They targeted two notoriously difficult fields: knot theory and representation theory. In knot theory, a central problem is telling different knots apart. Imagine two tangled pieces of string. How can you be sure they aren't just different versions of the same knot? Mathematicians use invariants, properties that don't change no matter how you twist or deform the knot. Some invariants are algebraic, related to the knot's twists, while others are geometric, related to its shape. For years, mathematicians suspected a link between these two types, but no one could find it. The researchers trained an AI on millions of knots, feeding it all their known invariants. The AI's job was to predict one specific algebraic property. Using a technique called saliency maps, which highlights what parts of the input data the AI is focusing on, they could see which other invariants the AI found most useful. To their surprise, the AI consistently zeroed in on specific geometric properties. Guided by this AI-generated hint, the mathematicians discovered a completely new geometric feature they called the natural slope. This slope directly connected the geometric world to the algebraic world, establishing a brand new, unexpected theorem. At the same time, another mathematician used the same AI framework to tackle a 40-year-old problem in representation theory involving objects called Kazhdan-Lustig polynomials. These things are foundational to understanding high-dimensional symmetry, but they are monstrously complex. I was trained to find a link between these complex polynomials and much simpler diagrams called Bruhat graphs. The model learned to predict the polynomials from the graphs with incredible accuracy. This success led the AI to a powerful new conjecture, that these incredibly complex objects could be calculated from the far simpler graph structures. It didn't solve the original problem, but it provided a completely new, more manageable path forward, a breakthrough born from the AI's pattern-finding ability. It's like having a muse that can see connections the human mind might miss. Another project, aptly named the Ramanujan machine after the famously intuitive Indian mathematician, is designed specifically to do this, to scan through numbers and discover new formulas for fundamental constants like pi and e, automating the very first creative step of discovery. Generating ideas is one thing, but the ultimate test in math is the proof. And this is where another DeepMind creation, alpha geometry, made headlines. In early 2024, it was announced that alpha geometry had solved 25 out of 30 geometry problems from the International Mathematical Olympiad, a competition for the world's most gifted high school students. This is a performance approaching a human gold medalist, and it blew the previous AI record of just 10 problems out of the water. The secret to its success is an innovative design called a neuro-symbolic architecture. Think of it as combining two different modes of thinking. First, there's a neural language model, which acts as the intuitive part of the system. Trained on vast amounts of data, it's great at recognizing patterns and can quickly suggest useful geometric constructions, like add this point here or draw this line that might lead to a solution. It provides the creative spark. Second, there's a symbolic deduction engine, which is the rational part. It operates on pure, formal logic and a set of predefined geometric rules. It takes the intuitive suggestions from the language model and rigorously tries to build a step-by-step, verifiable proof. This hybrid system works in a loop. The symbolic engine tries to solve the problem. If it gets stuck, it asks the language model for a hint. The language model suggests a new construction, which opens up new logical paths for the symbolic engine to explore. This repeats until a complete, logically sound proof is found. Perhaps the most revolutionary part was how it was trained. A huge bottleneck for AI in math is the lack of training data. Alpha geometry brilliantly sidestepped this. It generated its own data, 100 million unique, synthetic geometry problems and their solutions from scratch. It taught itself geometry without needing a single human example. This proves the neurosymbolic model is a robust and scalable path toward advanced AI reasoning. While systems like alpha geometry aim for full autonomy, another quiet revolution is happening at the interface between AI and human mathematicians. This is happening in the world of formal proof assistants like Lean. A proof assistant is software that lets a mathematician write a proof in a formal language that a computer can check for logical correctness, step by step. This guarantees the proof is absolutely 100% airtight, with no human error. The problem is, this process, called formalization, is incredibly tedious and slow. This is where AI is becoming a game changer. Researchers are now building AI co-pilots to work alongside mathematicians inside these systems. Projects like Lean Copilot integrate large language models with the Lean Proof Assistant. The workflow is transformative. Imagine a mathematician is working on a complex proof and gets stuck. Instead of spending hours searching for the right next step, they can ask the AI copilot. The AI, trained on massive libraries of existing mathematical proofs, can suggest the next logical step, or even try to complete a whole chunk of the proof on its own. And here's the crucial part. Any suggestion the AI makes is immediately checked for correctness by the Lean system itself. This acts as a perfect filter, catching any of the famous hallucinations or logical errors that language models are known for. It creates a safe and incredibly powerful collaborative environment. Early results show this can automate over 74% of the manual steps in a proof. As Fields medalist Terence Tao predicts, it will soon be common for researchers to simply explain a proof's high-level strategy to an AI, which will then handle the laborious task of formally writing it out. The AI doesn't replace the human, it augments them, freeing them to focus on creative strategy. For all these stunning successes, we have to be realistic about the limitations. The biggest issue is the hallucination problem. LLMs are designed to generate plausible-sounding text, not to be logically rigorous. This means they can produce proofs that look flawless on the surface, but contain subtle, fatal errors. A study called Proof or Bluff gave problems from the USA Mathematical Olympiad to top-tier LLMs. They failed spectacularly, with most scoring under 5%. They made basic logic errors, like generalizing from a single example, and confidently claimed to have solved problems when their reasoning was deeply flawed. This highlights a critical gap. Today's AI is good at giving answers, but it struggles with providing the rigorous, verifiable reasoning that is the bedrock of mathematics. This leads to the deeper question: is this true creativity, or is it just extremely advanced pattern matching? So far, AI seems to be an incredible muse, spotting connections that inspire human creativity, but it isn't yet originating deep, conceptual insights entirely on its own. The consensus among mathematicians is that AI is not a replacement, but a powerful new kind of collaborator. The future mathematician will likely be a strategist, someone who asks the interesting questions, guides the AI's search, and interprets its often non-intuitive results. The AI will handle the heavy lifting, the endless calculations, the formal verification, and the search through vast spaces of possibility, freeing humans to think on a more abstract, architectural level. The revolution isn't that machines are becoming mathematicians. It's that the practice of mathematics itself is expanding to include a new, non-human form of intelligence. This partnership between the creative human and the tireless machine promises to accelerate discovery and reveal truths in the mathematical universe that we are only just beginning to imagine. Thanks for listening to Fun Facts Online.